In this talk, I'll be going over some techniques for performing inference in complete graphs, including a novel technique I call diversity-based sampling. Graphical models provide a way to encode probability distributions and their underlying independence assumptions in a convenient way, so that inference on a distribution can be performed using techniques from graph theory. A graphical model generally consists of a set of nodes V that represent random variables in the distribution, and a set of edges E that denote conditional independence assumptions between the random variables. For instance, in a virology model, a patient's height or alma mater usually has no effect on whether or not they catch the flu, which is denoted by a missing edge between these two variables. However, exposure to other sick patients greatly increases the probability of infection, so we add an edge between the occupation of the person and whether or not they have the flu. Low-tree with graphs such as these are convenient because exact inference is tractable. In fact, it's exponential in the tree width of the graph. But what happens when we want to perform inference on a complete graph? A complete graph consists of one large clique and has tree width n-1, where n is the number of variables in our model. We could use a technique like a tree approximation, or we could use sampling-based inference like Markov chain Monte Carlo, but the problem here is that the joint distribution can be complicated because it's not decomposable. This problem is obviously difficult, but why even consider complete graphs? Consider the task of summarizing a document. We could represent the inclusion of a particular sentence in the summary with a random variable xi. Xi is 1 if we include the sentence in the summary, and it's 0 if we don't include it. Now, including any one sentence in the summary influences the probability of including any other sentence, because in a good summary, we want to maximize coverage of our document, but we also want to avoid redundancy. Therefore, our graphical model is a complete graph because the distribution it represents encodes all of these inter-sentence interactions. If we have a set of V sentences, the joint distribution is then defined over a binary vector with length equal to the cardinality of V, and it does not decompose. We want to design our distribution to assign high probability to what we deem to be good settings of x sub c, where x sub c is the single clique in our graph. In this particular case, we want the mode of our joint distribution to be the best possible summary for this document, one that values coverage and diversity. Finding the mode in this kind of joint distribution is NP hard. However, if we are able to sample the joint distribution, we expect to get samples x sub c that have high probability. The problem is, how do we define the joint distribution in a form that's easy to sample, especially for problems like these where we value coverage and diversity? One distribution that corresponds to a complete graph is the determinantal point process, or DPP. Any positive semi-definite matrix L defines a DPP, and in general L is symmetric. The entries along the diagonal correspond to the quality of item I. For instance, in the summary test, the quality may correspond to the degree of coverage of our document for a particular sentence I. Quality corresponds to unary potentials in our graph. The off-diagonal entries correspond to the similarity between items I and j and are equivalent to pairwise potentials. Now, because DPPs are generally defined over sets, for notational convenience and for the remainder of my talk, I'm going to use a mapping between a particular instantiation of xc and a set A. We say that the set A contains item I if the random variable xi is 1, and I is not in A if xi is 0. The joint distribution specified by the DPP is proportional to the determinant of the submatrix LA, where LA consists of the rows and columns of L corresponding to the items in A. For instance, if items I and j are in the set A, and A only consists of items I and j, then the DPP probability is proportional to this. Intuitively, this makes sense. The higher the quality of items I and j, the more likely it is we see this set. However, the more similar or redundant items I and j are, the less likely it is that we see this set. There exists a polynomial time algorithm to sample a DPP, but it's cubic in the number of items in our ground set, so DPP sampling is still slow for large sets of items. However, a DPP is a log submodular distribution, so we can use techniques from submodular analysis to approximate a DPP. Submodular analysis is concerned with set functions which take a discrete set as an input and returns a real number. All submodular functions obey this property, which is the fact that the marginal gain of the function for a particular item is less, given a larger context. As an example, consider a factory that manufactures paint. It's much cheaper for the factory to produce green paint if it's already producing yellow and blue paint. Otherwise, if the factory is only making blue paint, then they must also manufacture yellow paint to make green paint, thus increasing the marginal cost of producing the green paint. We can compactly represent this marginal gain with this form of the submodular gain function, or this form of notation for the submodular gain function. The distribution induced by a DPP is a log submodular distribution. If you recall that equivalence between xc and a, we can map the DPP distribution to a submodular function if we take the log of the distribution. This is important because we can use submodular maximization techniques to also approximately maximize the DPP distribution, thus giving us a likely setting of xc. However, we cannot find the max of fa, or equivalently the mode of the joint distribution, unless p equals np. Instead of finding the maximal value of our function, we can use some approximate submodular maximization techniques. One of these techniques is the greedy algorithm, which is guaranteed to achieve a fraction of the maximum function value. The greedy algorithm grows a set by, at each step, greedily adding the item with the largest marginal gain, given the current set A. So for DPP maximum a posteriori approximation, we use the logdet as our submodular gain function. The problem with directly running the greedy algorithm on the DPP distribution is that evaluating the determinant has cubic complexity, so the problem is still intractable for large ground sets. Instead, we could use a second-order submodular approximation to the log determinant. This approximation has bounded error when compared to the exact log determinant function. The gain function is then this relatively simple equation, and in fact the gain decomposes as a sum of pairwise interactions. So by using a dynamic programming approach, we can evaluate the gain for one item in constant time. Using this gain function, we arrive at my diversity-based sampling algorithm. This algorithm is similar to the greedy algorithm except for two modifications. The first being that this is a constrained algorithm where we force the selection of k items, regardless of whether or not the gains at a particular step are positive. The second is that instead of taking the item with the max gain, we instead form a distribution over the gains and sample from this distribution. The greedy algorithm itself is deterministic, but we want a stochastic version of it so that we can draw multiple samples from some joint distribution. Using the exponential function ensures that we may select an item with negative gain, albeit with low probability. The overall complexity of this algorithm is squared in the cardinality of our ground set, as opposed to cubic for DPP sampling. Now that we have our diversity-based approximation to DPP sampling for complete graphs, we should test it to make sure that it achieves similar performance to DPP sampling. We can first look at a qualitative comparison between these methods. In this experiment, we take all of the points in a discrete 2D grid as our ground set. Our complete graph then consists of one node for each point in the grid, with a pairwise similarity potential between each point to every other point. We sample a subset of size k either randomly, with DPP sampling, or with DBS sampling. The qualities of all the points are equal to 1, but the similarity between 2 points is the Gaussian distance between them. Taking a random subset ignores these similarities and results in clumping, leading to a non-diverse set. Both DPP and DBS sampling select a much more diverse set with less clumping, although there is slightly more clumping in the DBS sample. In this next experiment, we have a set of pairs of transcripts generated by opposing politicians during the presidential debates from 2012. The goal is to select pairs of sentences from these transcripts, with one sentence from each politician in a pair, so that the sentences within a pair are similar, and so that the overall set of pairs summarizes the debate succinctly. The quality of a pair is related to how well the sentences in the pair match, and the similarity between two pairs is determined by the TF-IDF cosine distance between them. We can see from the left figure that both DBS and DPP sampling achieves a much higher value of the joint distribution over the complete graph when compared to a random subset of size k, with the performance of DBS and DPP sampling roughly equivalent. However, DBS sampling is much faster when compared to DPP sampling, as we can see from the time ratio in the figure to the right. The reason there is a dip in the time ratio is that, for low k, the eigendecomposition needed to sample from a DPP is prohibitive. In addition, DPP sampling is cubic in k, so as we increase k, DPP sampling becomes slower. In this next and final experiment, I look at the performance of DBS sampling for diverse dropout. Dropout is a form of regularization for deep networks, in which the output of some random set of units in the network is set to 0 for each gradient descent update. Dropout aims to prevent correlation or coadaptation between the behavior of units, which can reduce the functional expressibility of the network. Instead of selecting a random set, diverse dropout targets coadaptation by selecting a diverse set in terms of the weights entering each unit in a layer. Theoretically, this diverse set has little coadaptation, so we drop it out. This results in the non-diverse and coadapted set being trained, which hopefully reduces the coadaptation of the overall network. The similarity kernel L is formed as the inner product of the weight matrices entering a particular layer. Again, we see that DPP and DBS sampling are both preferred to a random subset of size k, and DBS sampling is much faster than DPP sampling for this experiment. Thanks for watching this presentation, and I hope you check out my report if you're more interested in this subject.